Here's our continuation of some beginning concepts of triangles. We're going to talk about remote angles. Remember when we just defined exterior angles that we talked about an exterior angle as being formed by the extension of the side of a triangle. There's the extension of the side. And that it would also be adjacent to the interior angle. So this is the remote angle formed by that extension. Well, sometimes I'd kind of like to talk about the others. This one's adjacent to it, so I could talk about it as adjacent, but what if I want to talk about these two over here? These two angles over here. These are the ones that are not adjacent, the ones in the triangle that are away. They are not adjacent, they are non-adjacent. And what we call them is remote, because they're far away. Remote means not close. So these two angles are remote angles. That's the definition. They are away from the intersection that we're talking about. Here is our extended line, our exterior angle, and these are remote angles by definition. Okay. Get you another piece of paper. I've got me a pink piece of paper here. You're going to do the same thing that you did before. Go ahead and make a dot on any three sides. Connect it to make a triangle. So I'll do that. We're going to also draw a line in our cipher. Don't cut this thing apart yet. Don't tear it apart yet. We're going to do something with it first. So this one's going to be my other dog, Susie. Suze. S-U-Z. So take up in your cipher, draw a line, a horizontal line. You'll need some room on top of it or below it. I'll do on top. It doesn't matter. Don't put a point this time. Take your triangle. It doesn't matter what the orientation is. Choose one of the sides. But don't put it in the middle. Put it close to the left or close to the right. It doesn't matter. I'm going to put mine kind of close to the left. Take one side and have it to coincide with the line into the vertices. Two of them will be here on the line. And then put a dot up in the air where the other point is. So you'll have the vertices of your your triangle copied. So here are my three vertices. Here's the one that I copied from. Go ahead and draw these in to make a triangle. Label your triangle as a copy of whichever ones you had. So that would be, let's see, this one would be Z prime. If you've done that, go ahead and tear your triangle apart, same as you did before. So you can see the three angles. There is my Z. There is my S, and there is my U. We're going to work with the exterior angle here. So I don't need S. You don't need the one that's at the exterior, that's adjacent to the exterior angle. You need the two remote ones. So these are the remotes over here. Those are the ones you want. Take those, pick one of them, doesn't matter which. Paste it on again. You'll put it so the vertex is at the vertex and the line is on the line. Once you've done that, choose the other one. You might need to tear off some of the extra paper so you can see what you're doing. So this is going to be my U. And I'll make it a little smaller so I can tell what I'm doing. So notice it's going to just fit. How convenient, indeed. Put it in. You need to do this too in your cipher. Put it so that you can tell that it just, that it just fits. Okay. Let's look at what we've just done here. I've taken the two remote angles and copied them. Wait, this is the exterior angle, right? This whole big thing is the exterior angle. So go ahead and label that. So we have the exterior angle and the two remote angles, which are copied here. Hopefully you can see that the exterior angle is the sum of the two remote angles. And voila, yes indeed, I know you felt it coming, there is a theorem. The exterior angle theorem, the exterior angle is the sum of the two remote angles. We've just demonstrated it. Think about how you might prove it. That the sum of the three together is 180 and the other two is also 180. So do a little bit of manipulation around there. I think you can come up with proof pretty easily. All right, got some triangles here. Here I have a triangle. I'm going to take the same, I'm going to try to make one that's different. Okay, I want two angles to be the same and two angles to not be the same. So there we've got my blue-yellow angle is the same. I want that. And I want my red angle to be the same, but I want it to be a different triangle. Oh, wait. Oh, wait. There my blue and blue-yellow is the same. There my red-blue's the same. Oh, no, look. My red-yellow is also the same. I don't think I can do it any other way, and I can't do it any other way. And it happens to be, yes, indeed, another theorem, the third angles theorem. If two angles in a triangle are congruent to two angles in another triangle, the third angle has to be congruent. Oh, well, let's think how we would prove that. If I take 180 degrees, 180 degrees, I subtract the same thing from both of them, and then I subtract another same thing from both of them. Oh, my goodness, the same thing must be left, right? I think you can work that one out as a proof. Okay, well, I'm going to take my triangles now. I didn't do very good on the angles. I tried real hard to make different ones. I bet I can do it with sides. I'm going to do it with sides. So here I have some red ones that are the same, some blue ones that are the same, and some yellow ones that are the same. Indeed, I do. Well, I'm going to make different triangles out of these. I'm going to take one of each, but I'm going to make different triangles, different. Here I'm going to put together the blue and the yellow. I'm not going to do that over here. I'm not going to do that. I'm going to put together the red and the yellow. I am indeed. Okay. Okay, then over here, now I will stick the red one to that. You know, I'm just really confident that when I stick the blue one over here, it's going to be different, you know, because I made it different. I made it different. It's got to be different, right? Okay, let's look here. Okay, there we go. It kind of doesn't look very different. What you think? Well, they're not oriented the same. This one appears to be and is the mirror image of this one. Does that mean they're not congruent? Let's think. What was the definition of congruent? Same side lengths, same angles. I'm thinking it's the same side lengths and the same angles. You know, I tried really hard. I gave it my best effort to make it different, but it is not different. And this theorem, it is a theorem, I know you felt one coming, has a really clever name. It's like the side is the same, the side is the same, the side is the same, and the name of it is the Side-Side-Side Postulate. We could prove it, but we're not. If all of the sides of a triangle are congruent, the corresponding sides, then the triangles are congruent. Let's talk about another characteristic, another property of triangles. Triangles are stable. They're used everywhere, all over the place. Here's an example of a construction site where a home is being built. They've put some of the walls up. They want this wall to stay nice and sturdy and stable, so they've braced it with making a triangle. Over here, this one is in the middle of the living room. It's going to come out after they get it secured. But oh, look over here. Inside this wall, there are diagonals forming triangles. We live in Houston. In Houston, there's hurricane and the wind blows. And when the wind blows, the house needs to stand firm. If it's got triangles, there's a very good chance that it will stand firm. Most any walls in this city and about any place else are going to have triangles hidden in them if you can't see them. Look over here. You say, "What? I don't see any triangles on that wall." Yes, there are. They're kind of stealth triangles. If you look here, what needs to happen is that this point, the upper right, needs to be connected to the lower left, or the upper left to the lower right. Are they connected? You might say, "Well, I don't see a board there." Yeah, but they're connected uber good. This whole thing is in addition to the triangle that it forms. Does it connect here to here? It does. It does connect them. It does form a triangle, and it is stable. If you look at bookcases, you'll notice that bookcases always have a back on them. If they don't have a back on them, it's not going to take very long for them to fall apart. Here's an example of what happens when there are not triangles. This was in San Francisco after a earthquake. They didn't put triangles in. If you're not going to have triangles in a construction, you've got to have a lot of concrete or something to withstand nature. I'm sure that the engineer, architect, thought that this was sturdy enough, but it wasn't. When the earthquake came, it collapsed, crushing what was under it, which was quite unfortunate. Triangles make things stable. So let's look at a couple of examples here. Okay, this is not stable. It will go plop. It will go funk. And that will be the end of it. What about this? It is stable. There are no interior spaces that are not triangles. This one is more stable than the first one, but it's still not completely stable. Trapezoids are a little better, but they don't squash all the way, but they do still squash and collapse. Here we've got some guys on the gridiron. Who's going to land on the AstroTurf? I'm thinking these two guys might have a problem. There is no triangle brace on the bench. It is not particularly stable. A few examples to help you get into these. Angle relationships. You can look at these, and I'll put the answers up here in just a moment to show the angle relationships. Here's the answers. Here's a little bit of calculation using algebra. And here are the answers. Well, here, wait. Yep, there are the answers to the problems. And one more challenge problem. See if you can do that. It's not real easy. See if you can figure out what it's talking about. And then here's the answers to it. Okay. And here endeth the lesson.